Welcome. Thank you everyone for coming to this talk about CAFE, which is a new decision support system web tool for calculating historic and future climate altered extreme flows. And we're going to get into a lot about that, what that means, and how we've kind of approached this. And I will be presenting with Dr. Richard Palmer, my advisor from graduate school, and Costas is also on this project as well. So if you'd like to see more information about this project specifically, or anything related to kind of the principal investigations and the science-based catalog, this is on ScienceBase. It's on the USGS's page. The project started roughly around 2021. I had started grad school around 2019 and 2020, and we've been kind of researching this since and doing research about this since. The official project goals and kind of how we envisioned this going was really in 4 parts. We wanted to engage regional stakeholders to kind of ask them and identify needs associated with extreme hydrologic flows, mainly floods and droughts on rivers and streams. We wanted to improve estimation for those hydrologic extremes using kind of the methods we have, as well as machine learning. That was a big part of this project. We wanted to incorporate the impacts of climate change into these estimations, as the necasc does, and as is very important, as we've seen with Hurricane Helene recently, and today Milton is, as well as develop a decision support tool for incorporating climate change into these actual estimations, right? And this is a graphic by NOAA, which kind of shows how climate change may impact a lot of things, from storms to floods to droughts and fires. But to review and kind of summarize what we just talked about a little more, we wanted to improve estimation using traditional rainfall runoff modeling. For those of you who have worked on rainfall runoff models, there's a lot of different tools that help with that. The one we have used here is the precipitation runoff modeling system, which is the USGS's tool. We also wanted to improve estimation by machine learning algorithms where appropriate, and we want to emphasize where appropriate because a lot of people, I think machine learning is an end-all be-all and can be used for just about anything, but it's really just another tool in the toolbox. And we wanted to incorporate climate change into estimation at all of these locations, right? It's a big portion of this project. It's something we really wanted to emphasize as we proceeded. Some of the things we'll talk about today are some, I guess, common design metrics that we'll use as really when we talk about droughts and floods, we're going to be talking about these specifically. And these are just kind of examples of certain flood and drought metrics that are really commonly used in the public sector and things like that. So one is the 7-day 10-year low flow, which is the lowest 7-day flow that occurs on average once every 10 years. As well as the 100-year flood, which is the flood event that has a 1 in 100 chance of being equaled or exceeded in any given year. And we kind of have some nice pictures along with that, which is, as of this year, the Washington State Department of Ecology is actually looking into drought planning and preparedness, offering $1.7 million in grants. And as far as the flood goes, I think it was interesting to talk about, Helene was last week and Milton is today, right? Those are causing flooding on the rivers, and specifically this one's the Crystal River flooding. And so when we talk about droughts and floods, we also have to talk about gauged locations and ungauged locations. And I know a lot of people here aren't really, stream flow hydrologists, so I want to talk a little bit about this just to get an idea. So gauged locations are exact locations on rivers and streams where we have some type of stream gauge for reference. There's about 11,800 between the US, Puerto Rico, and Guam. And if you were to just blindly do that math and say, all right, 11,000 gauges in the US, we have about 3.1 million square miles in the US. For the state of Rhode Island, that would only be about 4 stream gauges. Now, there are more stream gauges in Rhode Island because we've carefully put them where we think is most important. But that just says that there's not really a lot of stream gauges and we can't gauge everywhere as of right now. So there are other methods to be able to kind of analyze those locations. And there's also things with remote sensing which help. But gauge locations provide really good historic data for direct stream flow analysis. And not all gauges have daily stream flow. They're also extremely expensive to kind of maintain. That's really the biggest kicker. One of our professors, Colin Gleason, likes to talk about that they're really expensive to maintain. If they freeze, what do you do with that? And then you have also locations near a stream gauge. So if it's not exactly at the stream gauge, but maybe just a little bit downstream that you're located and interested in, you can use that stream gauge data and just kind of have some minor tweaks, right? So every other location where we don't have stream gauge data or it's not close enough to a stream gauge to use, we consider them ungauged, and that's pretty much extremely prevalent in smaller watersheds and locations where it's really hard to, install stream gauges, things like that. And the calculations are handled very differently. So when we started this project, we had the idea to really incorporate climate change everywhere. And to be able to do that, we weren't able to just rely on just gauge locations and gauged kind of methodologies. So we wanted to kind of explain this a little bit and then proceed with both gauge and ungauged locations and the science behind those. So if you're at a gauge, I just want to briefly talk about this. I'm not going to run into the math too much, but if you're at a gauge, if you want to look at the 100-year flood, you can take the data from that gauge, which is the annual peak flows. So every year, the highest that river gets and the biggest stream flow that river gets, you take that one data point and you fit a line through it. And if it's only 30 years of stream flow data, which we have sometimes, you kind of have to extend that using some methods, as well as fitting an extreme value distribution to that data. And then we take that extreme value distribution and we extract the number we care about, right? And one thing that you can note is I just kind of walked through that methodology right here. Notice that in this case, it's 2,700 CFS, but just fitting the extreme value distribution, right? There's so many different answers you could have here that would mathematically be appropriate. Typically for the USGS and Bulletin 17B, which is what most people use, we would use log Pearson type 3, which is what we've kind of proceeded with. But then you get the 100-year flood, and if it's slightly downstream, you can, or upstream, you can use kind of a quick ratio to proceed with that. So I hope that makes sense. And obviously tools have been built to kind of use this methodology and incorporate that. PCAFQ is probably the most common one. It's a USGS program, which basically, if you look at a stream gauge, it does exactly that methodology with you, and it gives you the answer in log Pearson type 3, and you can play around with some of the distributions, as well as HECRAS, which is another really common one, which is more about kind of the channel routing. So when you take that stream flow number that PCAFQ gives you, you can kind of input it into this, this channel and see exactly how high the river may get. In contrast, 100-year flood estimation is a little different. We do exactly what we just did with every stream gauge we have data for, and then we fit a regression to it. So we know that we now know the 100-year flood at each of those stream gauges that we've calculated from all that data. And we also know that the watershed attributed to that is so big, right? In this case, this one's about 16.3 square miles, and we also have the station ID with that. But what we do is we just fit physical characteristics like the land cover, and sometimes climate, right? All of those things that could point us in the right direction to the 100-year flood, but don't necessarily calculate it using the methodology we just did, right? This is a statistical method. It's regression, right? Linear regression, as I'm sure you guys know. There's other ways to do that as well. And in this case, I went through a location in Rhode Island because I was presenting some of this work at the Rhode Island Flood Mitigation Conference and found that this specific location didn't really do a great job. But that being said, overall, the USGS presents some really good numbers for estimating these flows in locations that are ungauged, right, using regression. And there are a lot of tools to help do that. The most common of which is probably StreamStats. Many of you have probably used. It's used in classrooms and widely across the US. Natural resource managers use it all the time. I use it a lot for a lot of my work as well, but it's all based on solving regression equations, right? Somebody comes up with a regression equation for calculating the 100-year flood based on drainage area and land cover, and you can find that for your location. So StreamStats is really good at delineating watersheds, which is a tough thing to do in general, and giving you the physical characteristics you need to be able to put into those regression equations. And DFlow and SW Toolbox are also a little older tools, but they're still used widely, and they use the same kind of methodology, but they allow you sometimes to also build your own regression equations, which can be useful. So the problem with StreamStats, which we've kind of highlighted, it's a great program. Don't get me wrong, it is used widely and it's one of the best. But there are some things that I think, leave some things to be desired. And it's not recommended for larger watersheds, which is just some of the methodologies and the regression equations kind of break down. It's incomplete for a lot of states. Some of the people we've talked to over the course of this project don't have 7Q10 estimation for their state. So they asked us if we could help them design some things for that. Sometimes it's not ideal. This is the equation for, I believe it's Massachusetts, on how they calculate the 100-year flood. That's a tough equation to rationalize and kind of conceptualize as a hydrologic engineer, like I am. But the biggest thing that I would point out is that all it does is use historic data, right? If we have 100 years of data at a location, we get the 100-year flood from that, we fit regressions to all those 100-year floods we know of, and that's it. And again, that's a great way to do things, but now that we're thinking about climate change, we have to consider maybe only using historic data isn't the best way to approach this, right? Should we consider future things? And that's one of the biggest things this project has really tried to focus on. So methods for incorporating climate change, these are just two very kind of common ways to do this, and probably the simplest. That being said, for the physically based modeling, it's not exactly simple, right? So we get our emission scenarios, and then we create these giant global models, and then we only look at a specific location, like the Northeast, where I'm located, and then we have to kind of correct that data in case it's not great, right? This works great for the entire world, but that doesn't mean it works great for Amherst, Massachusetts. So we do some corrections there. Then we put it into a rainfall runoff model, which is what I primarily focus on. And then sometimes we even put it into some type of reservoir storage and other modeling. And that, as we go down the steps there, just builds and builds on uncertainty, because there's uncertainty with the modeling here. There's uncertainty when we're trying to correct the data for Amherst, Massachusetts. There's uncertainty in the rainfall runoff. And by the end, sometimes there's a lot of uncertainty with that. Versus ungauged locations, it's really, we use the regression equations the same way we had been. Which is, if the regression equations already include some type of climate variable, that means the regression equation has figured out maximum precipitation is one of the things that can be a really good predictor of this. So what if we change the maximum precipitation slightly as a tweak value to say climate change might be doing that, and see how that kind of works? And neither of these are the perfect methodology, but I think in unison, they give really good mathematics to be able to justify results and decisions to be built on those results. So we did some scientific studies for this project. I would say research topic 3 would be what we would normally talk about first, but I think it leads in really well into the actual decision support tool. So we've kind of pushed that back to third here, but we'll definitely talk about stakeholder engagement and kind of asking, the people who actually do this for a living and for their careers, what they needed and how they thought this could be put together, right? So for research topic 1, we built our own kind of regression-based statistical estimation. For research topic 2, we did more of the traditional rainfall runoff modeling. And then for 3, we looked at a specifically stakeholder input and building this decision support tool. So for topic 1, what I want to highlight is, instead of StreamStats, which does state-by-state regression equations, we built one for the entire Northeast. And we did that because we thought it would be pretty difficult to just do individual regression equations for every New England state and then make sure that they're all properly calibrated and then build them all in, when really what we're trying to do with this the most is add climate change. A lot of the regression equations already built into the Northeast in StreamStats do not have any climate variables. So it's hard to kind of use those as a basis for incorporating climate change when they don't exist. So the whole idea behind this was make an entire one for the entire Northeast and proceed with that. And then we also did traditional rainfall runoff modeling. So one thing that our stakeholders told us, and one thing we pointed out, is that if you were to take a rainfall runoff model, they're very complicated. You can build them at pretty much any location. A lot of programs have been made to build them at specifically stream gauges. Some have been made to build them at ungauged locations, but they're really hard to calibrate and validate. And if you just build this at a random location on a river, how do you know that that's working, right, for the past? If you just take one of these models and try it for a location that is gauged, you'll find that without calibration, it's not the greatest, and it's really hard to build good decisions off of. So we were thinking maybe we can apply machine learning to be able to calibrate these models at gauges and see if we pretended that we didn't have any, actual data there, if it would work that way. And one thing we kind of toyed with was, do we just do this for daily stream flow estimation? Do we do this for extreme flows, or both? Right. The point of this project was really to focus on extreme flows, and traditional rainfall runoff models are really built for daily flow estimation. That being said, daily flows also are what used for, high flows and low flows. So we can use rainfall runoff models to do that. It's just kind of one extra step. So building on those two methods, we kind of played around with how good they are. So a rainfall runoff model off the shelf, uncalibrated, is not very good, even for daily flows, let alone kind of extreme flows. But if we calibrate them to daily flows, it ends up being a pretty good thing to use. 0.4 to 0.6 is pretty good. So this being in the 0.52 range means your daily flows are a pretty good estimate using this model. As far as extreme flows, this is also kind of one thing we highlighted, is that calibrating this model really helped calibrate for extreme flows as well. When we look at stream stats specifically for droughts, in this case, the 7Q10, it's about the same. It's maybe even a little worse for kind of the stream gauges that we looked at specifically for just the drought that we're kind of analyzing here, as well as the random forest method from the statistical paper, which I didn't even really go into too much, ended up being also a pretty good predictor regionally compared to stream stats state by state estimates. Now, the rainfall runoff model, specifically calibrated with machine learning from the previous step, actually improved daily stream flow estimation a lot. The machine learning algorithm really helped with that, but it didn't really improve extreme flow estimation much. So when it came down to it, we found the regression models are pretty quick, cut and dry. They're trusted by a lot of people. They're built for the USGS, by the USGS, and they're just as good as kind of this method. And our calibration technique did not kind of compete with that at the time. So now we're going to talk a little bit about the stakeholder engagement on this project and how that really played into the final tool. So for this, I'm going to turn it over to Dr. Rick Palmer, who is my advisor and the PI on this project, and he's going to talk about that.
Great, Andrew, thank you so much for the first portion of this talk. And I want to thank everyone back in Amherst. I'm coming to you from the beautiful Northwest, from Seattle. And I just want to say I'm extremely excited about being able to present this material to you. We've submitted our final report to our USGS sponsors, and so I'm sure that will all be available to you shortly. So as Andrew mentioned before, it would have been wonderful if we could have talked about the stakeholder engagement first, but it was sort of intertwined with all of this project. And so we decided to focus on here. And after I finish, Andrew is going to get a chance to summarize a little bit, but also demonstrate the software that was developed. So I think all of you will find that very interesting. And I want to emphasize one other thing that Andrew said, which is these two challenges that we face. One is, how do you deal with estimating extreme flows at locations that have data? And then how do you do that same process at all the other locations that people might have interest in, which simply are not gauged and may or may not be anywhere close to a gauging station that's appropriate? And the second thing that he mentioned, climate change. We're sort of at this very difficult period of recognizing that flows are changing over time. And that puts us in our difficult challenge of how much of the historic data to use, because I don't think any of us ever really want to throw away data. But if we find ourselves in a very different environment than we've had in the past, particularly for extreme flows, it presents a real challenge. So as Andrew said, really the overall goal of this project was to develop this decision support system. But to do that, we had to go through the process, as Andrew described, of understanding how stream flows extremes are estimated now and what could influence them in the future. So all of our goals are basically associated with that, understanding how this is done in practice, how can we improve the methodologies, and then, if possible, to update a program with stakeholder feedback so that it can be useful. Andrew, next slide. So I just want to say a couple of things about engaging stakeholders. And this is really a topic of, I think, great interest to me and something I feel very passionate about. And basically, the climate science centers across the US, and I think particularly here in the Northeast, we've always, since our inception, understood how important it was to engage stakeholders in this process. And in many cases, those are natural resource decision makers. And there are many reasons for this, but I think some of them are actually obvious and clear. And that is really, if you want to create science that's going to be actionable, that your results are going to be usable, then it's always more efficient and effective to begin with the individuals who are going to actually be in a decision-making role. And so we think this is really important, and you'll see in a moment over time how we involved some of our stakeholders. And you can't involve everyone in every decision process. And so we needed to find a way to work with stakeholders. And in the past, we've used things like circles of influence and other kinds of ways. But I think our group of stakeholders really come from a specific group of potential users. And so I think over time in CASC, we found that one approach that works well is basically developing a user group or a working group. And that was the approach that Andrew and I took. And I think when the group you're working with has a reasonably consistent set of backgrounds or purpose, these working groups are extremely valuable. And let me just say that stakeholder definitions have changed over time. I think, we defined stakeholders in the past as sort of one of three groups. It's like people who are affected by a decision, or people who can influence the decision, or people who just have a general interest in the outcome. That was one definition of stakeholders. And I think now we think about rights holders and a whole variety of groups of people when we think about stakeholder engagement. I've been at this for a long time, and I didn't come from a social science background. So when I thought about stakeholders, when I was beginning, I conceived them more like this, Andrew. Next slide. That's what I thought a stakeholder was composed of: someone really engaged in eating a steak. Okay, so next slide. So we took a very, I think, consistent and simple approach to this, which we'll go through. And there's much written about how one should try to obtain knowledge from people to help them in the process of quantifying the way they make decisions. And so we used a couple of different approaches. And one was, we interviewed individual groups of people. And what I mean by that is we would contact a state agency or a federal agency, try to identify people who are engaged in the process of making use of these estimates of extreme flows. And in those cases, we might get one individual in an agency, or we might have gotten several individuals in an agency. But we had these sort of consistent set of interview questions to ask that individual or small group of individuals within an agency. And the purpose of that was to identify what their management needs were, and in a sense, a little bit more than that, sort of what environment they found themselves working in. And I'll probably mention this again, but these environments were often resource limited, whether that be time limited or whether it be financially limited. And so perhaps for a really large project, if you were looking at extreme flows, you might have time to develop a rainfall runoff model, or you might have time to do other things. But many of the people that we found and worked with really were given the task of estimating something at a new location quickly. And so you'll see that that's sort of the type of tool we came up with. So in addition to these sort of individual meetings with either an agency or an individual, we also had group meetings. And these were, I have to say, exciting, and people had different points of view, but they were really great for looking at overlaps in terms of needs, and also in identifying the differences that existed between users. And a huge advantage of having these group meetings is that you would discover synergies between groups that we hadn't identified before, simply because they weren't, quote, in the same room. And I should note, this is all during COVID. So the same room meant the same the Zoom meeting. Another thing that we did that we thought was quite valuable was to demonstrate the software as it developed in a repetitive fashion. That sounds awful, but to do it numerous times so that they would get a real feel for how the software was developing, and they could make specific inputs over time, so that we always kept, I have felt, headed in the right direction to meet their needs. And then finally, they were quite interested in being able to make use of the software. And so we tried to continue in our sort of knowledge acquisition and testing approach to make sure that the platform that we were using was going to be accessible to everyone. So it didn't require any different type of software that no one else would have, that over time the system would be sustainable and that it could be easily modified. And anyone who works on programming knows that easily modified may not always be easy, but at least build it in a modular fashion so it could be modified over time. Next slide. So the interviews we did in the Northeast, you can get a quick, I won't go one by one, but you can get a quick overview of this. We worked with hydrologists, hydraulic engineers, a small group of transportation engineers who were particularly interested in flooding, NPDES permitting folks, climate change specialists, fisheries biologists, and others throughout the Northeast. And most of those interviews occurred in 2023 or very occasionally in 2022. And then at the beginning of this, I was involved with a project involving changes in aquatic flows. And so I took the time to go out and interview people in Georgia and Idaho and Montana and Washington State. So the focus you're going to see today is totally on the Northeast, but we did get a chance to talk to managers and a wider group of people. Next slide. So just a couple of real quick takeaways from these meetings. One is that obviously many of them were already using tools. Some of these tools weren't used maybe for their end purpose, but there's a lot of great tools out there. And so someone might be using stream stats that delineate watersheds or calculate some physical characteristics in their basin that were useful for them to make a calculation that perhaps wasn't even part of the stream stats program. And also there's other tool sets out there, as Andrew mentioned, that were valuable. One of the things that we noted, and this was not only in practice, but in the academic literature, that it became obvious that in many cases, you could see trends in terms of extremes, low flows getting lower and high flows getting higher. And so this conflict between using a complete database and a shorter database was evident in the discussions that we had with people over time. And I guess realistic, although a little bit sad thing highlighted in red here, is that very, very few individuals that we worked with had sort of go-to procedures for incorporating climate change into how the extreme flows might change over time. And we all know that's a very complicated question, but many people were left really without a next second step of how they might approach that particular problem. So next slide. Over with our time working with the stakeholders, I would say, focused on three primary things they wanted to look at. And so they were very interested in this relationship between gauged and ungauged. And so you'll see in the demonstration, one of the first things we made sure was that there were some simple techniques for extrapolating streamflow extremes from gauge stations to ungauged stations. And Andrew will sort of demonstrate that. And that's a very common method when it's appropriate. And he might say a few words about that. Because so many of these models, as Andrew said, are based on linear and nonlinear regression models that are contained in programs. The managers often didn't want to go back and look at the 20s and 30s and 40s and 50s in terms of calibrating those models, but would be much more concerned about what's happened in the last 30 to 40 years, or maybe 20 years. And so that was not available to them in general, since typically the whole historic record is used to calibrate these regression models. And again, almost no one we worked with had the luxury of building a rainfall runoff model in a time frame in which their decision had to be made. And for the practitioners here, I'm sure this is not news to you. It happens all the time. And so what they were looking for was a particular technique that would allow them to get, one might argue, a first order estimate of how much things might change over time. And so we made use of other research that's been done by in CHRP, the National Cooperative Highway Research Program, where they were looking at applying climate change to hydrologic or hydraulic design. And again, for most of that, it was at the upper end, the high flows rather than the low flows. So Andrew, I think I can turn it back over to you. Go to the next slide.
Sure. So the way we did end up incorporating climate change, we built this to be able to look at gauge data and also build the regressions for history, but we still needed to incorporate climate change in some way. And so the way we've done that is they were particularly interested in using the regression models essentially with new climate data. And a lot of those had never been built for stream stats with climate data. But we didn't just do that as well. We did a physical model with rainfall runoff models throughout the entire Northeast, and we built this kind of regression model in parallel, and we played around with both. So we ran the rainfall runoff models with climate projections into the future, and we ran the statistical model with climate projections into the future, and we kind of compared the two. And the statistical model, especially for the low flows, was pretty good predicting as far as the rainfall runoff models also. So we compared the two and found that this method was a pretty shorter, kind of accurate way to do this. And that was really good. We were excited to see that. So we built this into the program where you can kind of change the temperature in here independently of the precipitation and say, well, what if precipitation changes by negative 20% or 20% more? Right? Versus temperature, we've gone from kind of 0 to 20 here and saying that, well, if temperature rises, how is that also going to impact the model? And we've given some kind of some estimates from our own analysis here about exactly how much temperatures will change based on kind of the RCP scenario, right? Most people are familiar with the RCP scenarios, especially the ones we had talked to, knowing that climate change was kind of a problem for water resources. And these are all built on 9 GCMs that we found appropriate for the Northeast. When it comes to the high flows, the way we've incorporated that is we incorporated temperature directly, but we found it most appropriate given our physical models, right? They gave us some justification for doing this, that if we use the Clausius-Clapeyron kind of relationship, that the models gave much better results rather than just using the maximum precipitation straight from the climate projections, right? Future climate is tough to estimate. A lot of the models have different results. And as far as precipitation goes, that's more uncertain than temperature, right? It's a second order uncertainty because precipitation also relies on temperature. So everyone felt more comfortable as far as we talked to, as well as our physical models kind of pointed in the direction that if we incorporate temperature directly, but we incorporate precipitation using kind of the Clausius-Clapeyron relationship, which says a 1 degree Celsius change can increase atmospheric humidity of about 7%. So that means about 7% more water in the atmosphere. So when it rains, it should rain maybe 7% harder. We can build those into the model. So since that comes directly from the maximum temperatures, we just built in temperature for the high flow part of the program. So you can play around with the temperatures and it will kind of generate new values based on the statistical model with some physical model as a backing, right? So that was all the science, but we needed to put together a decision support tool now, right? So we actually split it up into kind of 2 links. There is the high flow tool and the low flow tool. We did this because a lot of people that we talked to and our stakeholders, really their job only focused on one or the other. Very few people had to both look at droughts and floods. So we kind of built this out so that you could follow the same procedure in both tools, but for the people that only needed the low flow one, they wouldn't be confused or overwhelmed with kind of the high flow stuff and getting confused. But we built this tool out, and it is online. You can go to it right now if you wanted to, but I'm only going to show kind of screenshots from it. It is an open source tool, so a lot of people can go to the web page at any time. But it says, welcome to CAFE, which is the calculation assistant for flow extremes. And it's built into really 3 parts, which is directly from what we thought the science was, as well as what our stakeholders requested of us, which is that the gauge flow tool is looking at just history. It's mimicking the peak FQ program, which is saying if we have 100 years of data at this location, can we get an 100-year flood estimate from that? And there really is no climate change built into that, but this is just something where you'll be able to quickly get the 100-year flood using our program. And then after that, you'll have the option to apply climate change at the end, as well as the ungauged flow estimator. We have kind of the same thing there. If you're looking at a location you don't have data for, especially like New Hampshire was one and Vermont was one. In Vermont, they don't have ungauged 7Q10 estimation built into stream stats. So we did that for them, as well as using the last 30 years of data. And then you can get a number from either of these things. And then you can apply climate change using those tool kind of science that we just explained in the last 2 slides. So I walked through kind of an example here, but I put in a gauge, and you can put in a gauge as well, one that has daily stream flow, and it says you hit retrieve stream flow data, and it says download was successful. And then it tells you the first date of stream flow and the last date. This is, again, the location in Rhode Island with about 17 years of stream flow data, but I thought it was a good one to use. And of course, people want to see the raw stream flow data before we do anything, right? They want to see if there's anomalies, if there's gaps in the data because of some reason, and just how long it's around. So we have the tool where you can play around with this. As you slide these sliders, the graphic automatically updates. So if you only want to look at the last year because something happened, like a really big hurricane, you can absolutely do that by playing around with this. Or if you only want to look at flow ranges, right? Flows above 1,000. How many times did that happen? You can drag this to 1,000 and it'll auto update as you go. And it also spits out like minimum, maximum, and quantile flows here. So the median flow and those things. So we continue with this example, and we also plot the annual peak flows. So one thing that's really important is if the annual peak flows seem to be increasing, that might point in the climate change direction, or just land cover changes, or just general changes here. So we wanted people to be able to look at this and say, well, are things starting to change, right? Are we seeing these things? So we've used the Mann-Kendall test, which is a pretty simple methodology of just looking at if things have started to kind of change from the beginning to the end. And then it also plots the 25-year flood, the 50-year flood, and the 100-year flood on this pretty graphic right here. And of course, for what we're looking at, we're kind of focusing on the 100-year flood. And this location happens to be 2,232 CFS. And then the last thing you can do is once you have this 100-year flood, you can kind of do an area to area flow scaling. So if this is slightly upstream or downstream, you may not want to use this exact flood. You might want to use a slightly smaller or slightly bigger flood based on if your watershed is getting bigger when you go downstream, or if it's getting a little smaller when you go upstream. For the ungauged portion, we also have it contacting stream stats directly. So I always recommend to do this in parallel with stream stats. But if you have a point on stream stats that works, like this one right here, the latitude and longitude, if you have a point you know works in stream stats, you can also put it into this program and it'll do the same methodology, but with our kind of tool. So you hit calculate and it contacts StreamStats API, and then StreamStats comes back and says, hey, we got you everything you need, which is area, elevation, slope, forest percentage, wetland percentage, and the 100-year flood directly from StreamStats for the locations it is available. For states that's not available, it just comes up blank. But for Massachusetts, we have all of these things, and for Rhode Island, we have these things. And then the next thing is you can put them into kind of our regression estimator. So you put the watershed area in, elevation, slope, and you hit calculate. And we have kind of, for the high flows, we have this estimating the 100-year flood using our regression equations we've developed, as well as StreamStats has their own estimate right here. And so for this location, the best one ended up being the random forest machine learning algorithm, which was kind of straight from our paper. But for the low flows, because they had asked for the 30-year flows, we have kind of 6 estimates there, which is the regular full record 7Q10 flows, and then we also have ones built on just the last 30 years of data, which is what a lot of people asked us to do. Using the last 30 years of data was something that like a lot of people had told us they had started to do. And again, it was supported in literature in 2019, but people had started doing it even before then from what we kind of heard. And they wanted regression equations just built on that, which StreamStats isn't really that editable and it always uses the full record. So we built that into our low flow program. But the climate change portion, just as kind of a I guess the summary here, you can take that number that we've gotten from before. This is directly from the gauge, right? If we didn't have the gauge, we could use the ungauged number. So you can put your 100-year flood in here, and then you can play around with essentially the slider, and that will change all of the math in the background and give you kind of updates. And what we want to highlight is, again, this is built on the statistical model and using the physical model for some justification, because we didn't want to blindly apply a regression and just say that's the answer, right? There's a lot of tools we have, and so we wanted to kind of analyze this further. And so one thing we found is that kind of on average for this location and overall, the 100-year flood is changing by about 5% per every degree Fahrenheit. So that might be a number, you can talk at a dinner parties if you want to, but what the idea is that for every kind of temperature increase of 1 degree Fahrenheit, we're looking at maybe a 5% worse flood. And if you think about it in terms of the Clausius-Clapeyron relationship, right, 7% more water, all of that water may not turn into the flood. Some might get absorbed into the ground and runoff and things like that. So this number seems reasonable from every justification we've kind of had for it. We have users of the program, which is really nice. I kind of want to highlight maybe EA Science Technology. I presented this at Rhode Island Flood Mitigation Conference, and I had 2 people email me from that, one of which worked at EA Science and Technology. He actually turned out to be one of the co-authors on the original paper that was highlighted by the National Cooperative Highway Research Program. And he said he was really happy to see someone had turned his kind of methodology into a program, and they are currently using it for kind of what they're doing. He made me walk through all the science with him over basically 8 emails. But I'm just happy to know that they are using this and they're getting ballpark numbers and they're comparing it to rainfall runoff modeling and all those other things. And so I was really happy to see that. And so we also have some of our stakeholders we know that are using the program. The EPA likes the 30-year stuff because, again, that was something they've been doing for a long time, as well as New Hampshire Environmental Services and some Division of Fish and Wildlife for Mass. So final thoughts, because we're kind of cutting it close on time, is that resource managers that focus on these extreme flows don't typically use rainfall runoff modeling. They're hard. I've built a career on using them, and they're not the easiest thing in the world for sure. At gauge locations, they're just difficult and time consuming. At ungauged locations, it's hard to justify that they're even working, right? So when you have someone who's working on permitting specifically and things like that, wastewater withdrawals and all those things, they go through a public commenting process. And so they've been using these regression equations for 20 years, 30 years. And so trying to incorporate climate change, if you start putting that in on a random Tuesday, it's hard to justify to those public stakeholders. But if they say, hey, we're just kind of updating our regression equations to now, consider the fact that we might have a little more rainfall, that is something that is a little easier to justify to public stakeholders. And one of the big reasons that our stakeholders said they'd rather see kind of the regression equations driving this. And last but not least, as we talked about, resource managers know that climate change will impact flows and they want to do so, right? Everyone we talked to was like, yes, we know that and we want to, it's hard and we don't really have a lot of trustworthy tools to do so, and we don't have a ton of time. So there's a lot of opportunity still here to be able to kind of work on this program, or as well as developing other tools. And one thing that I kind of came up with was, why don't we make a rainfall runoff model where if you click on a location, it builds a rainfall runoff model there, kind of like we've done with StreamStats with regression. That is a tough thing to do. I know the USGS has looked into that multiple times, but a tool that could do that would be really advantageous as well. And that's what we were kind of targeting with topic 2, right? If we can calibrate a model at an ungauged location, we can build a model there and we can make sure this is working and then incorporate climate change with the rainfall runoff as well. Thank you all. This was, provided by the necasc for a decision support system, and we'll leave it open to questions for the next 10 minutes. But we're really happy to be here and happy to answer any questions you may have.